Hey. Hello, and sorry, that was me being anxious to get started, everybody. Welcome, welcome, welcome. Hi, everyone. Welcome to Science Friday. This is our first Down to Earth Mission Control Live for Science Friday, and I am Sandy, your Education Program Manager. I'm joining you from New Jersey today, and I would love to see where you're joining us from. So if you could go ahead and just add that to the chat. It looks like we have a few people that have already started. Hi, Joanne from North Carolina. It's really great to meet you. Make sure that you are signed in. Oh, you know what? I'm sorry, I have lost my script. But make sure that you are signed into YouTube so that you can chat with us. So that is a common thing. Just make sure that you have actually signed in with an email address and you'll be able to send us questions, share where you're from, and all of that kind of good stuff. So if you don't know us, we like to say Science Friday is your one-stop shop for all things science news. We're very well known for our weekly science radio show, which is broadcast every week on Fridays at 2 p.m. Eastern. So you'll be able to tune right into that when you're done here. You can listen to us live on your local radio station or by visiting sciencefriday.com and clicking the listen banner right at the top. It's a really convenient way to listen to the show. But today we are here for Science Friday Educate, and I'm really glad that you joined us. We'll be hosting these down-to-earth mission control live events every week in October at the same time at 1:45 Eastern, 10:45 Pacific. We're also sharing some great design challenges over on our website every week. So if you go to sciencefriday.com/down-to-earth, there it is, you'll be able to get those great design challenges. They use common materials. They're easy to do. They're great for classrooms or for home. And we have a ton of great educational activities over on our Science Friday page. So just click on Educate and you'll see a library of great science and STEM activities that you can do anytime, anywhere. As a kind reminder, before we get started, Science Friday is committed to providing a welcoming and harassment-free environment for all members of all ethnicities, ages, gender, trans status, sexual orientation, physical ability, national origin, beliefs, and any other dimension of diversity. We've created a code of conduct, which can help you, which you can read in its entirety on our website, I believe, under community. And we just believe in setting really clear expectations as a necessary part of a respectful community. I'm going to slow down and breathe. Here are some of the basics just to remember as we interact today. Please be supportive and respectful when speaking to one another and asking questions in the chat. Share generously and listen closely. You can add your thoughts whenever you want in that chat, even if they aren't strictly questions for our guest. It's totally fine to interact with one another. Try to stay on topic. Today, we're going to be talking about space exploration and astrobiology and all things that are happening in the universe and all kinds of topics related to that. And we do reserve the right to have you leave or to ban you if anyone starts behaving in any kind of demeaning, discriminatory, or harassing behavior. I don't expect that's going to be an issue, but I want to make sure that everybody knows that they are safe to express themselves here. Thanks for sticking with me for all the important details. With that, let's welcome to the stage our scientist for today's live stream. Welcome to Dr. Mike Wong. Dr. Mike Wong is an astrobiologist and planetary scientist at Carnegie Science's Earth and Planets Laboratory in Washington, D.C. Thank you so much for being here, Dr. Mike.
Hi, thanks for having me, Sandy. It's so good to be here, and I'm excited to answer all of your questions.
Wonderful. So let's start getting those questions into chat. Dr. Wong, I know that you brought a little bit of information about your work. Why don't you share that with us so that we can kind of familiarize everybody with what an astrobiologist does?
That's right. Yeah. So I'm Mike Wong. I study planetary science and astrobiology, which means I'm broadly interested in getting to know our cosmic neighborhood and to try to look for signs of life beyond Earth. And so I thought I'd just introduce myself by telling you where I was and what I was interested in when I was around your age. When I was a young kid, I was very interested in science fiction more than science. Actually, I grew up watching a healthy dose of Star Trek. And for those of you who are familiar with the Star Trek universe, you know that Starfleet's mission is to explore strange new worlds and to seek out new life and new civilizations. But when I was a kid, there wasn't really a way to do the second one of these. The opportunities to look for alien life were, few and far between. But I did find a way to do the first one, to explore strange new worlds. So when I went to college at UC Berkeley, I was able to study and major in planetary science. And one of my favorite research topics when I was in college was this weird form of ice called superionic water ice. Superionic water ice is actually not so weird. It's just water. As we know, water is H2O. And so superionic water is still just H2O. As we know here on Earth, water can take many different phases. So we're familiar with it being a gas that wafts around in the atmosphere. Water can also condense into rain droplets that rain on top of us, and we can find flowing in rivers and in the ocean. And then water can also freeze into a solid. But on the planets Neptune and Uranus, it's thought that there's a completely different phase of water that we call superionic water ice. And so studying this exotic phase of matter was something that really piqued my interest in college. When I went to graduate school, I decided that I really wanted to study how planets and life might co-evolve. And one of my favorite projects in graduate school at Caltech was thinking about the emergence of life, how we are all sort of children of our own planet. So what geochemical scenarios might have produced that origin of life? And one of the leading hypotheses is that we originated at hydrothermal vents at the bottom of Earth's early ocean. And that was a fascinating topic to study. As I graduated from my PhD and throughout my entire career, I've maintained a very strong interest in science fiction. Here I am at the end of my PhD wearing a Star Trek uniform still. So it's really been a source of inspiration for me throughout my entire life. After I graduated with my PhD, I became an astrobiologist at the University of Washington, where I took my interests beyond our solar system to think about planets that orbit other stars other than the sun. So this is what we call exoplanets, and I was particularly fascinated by Venus-like exoplanets and how their chemistry changes when you put them around a different type of star. This is sort of like changing the light bulb in your room from a nice white yellowish light to maybe like a different color, like red. And just like you would get a different mood in your room, the chemistry on a planet orbiting a different color star will change as well. And we wanted to study that. And where I am now at Carnegie Science, I'm really broadening my horizons as a scientist. I'm learning how to apply data science and machine learning and artificial intelligence to my work in planetary science. I'm also thinking about how to include philosophy of science and ethics into my work on astrobiology. And of particular interest to us today, I'm also working on reinforcing the overlap between space science and environmental science. And I look forward to talking with you all about that over the next 20 minutes or so.
Thank you so much, Dr. Wong. That is so fascinating. Like you, my dad absolutely adored Star Trek, and we watched it every opportunity together. And that is a big part of why I went into science. I just went into the biochemistry side. I was excited about all the different kinds of creatures that were potentially out there in the world, or universe. As we're waiting for folks to post, I hope I could take the opportunity to maybe ask you a couple questions that I've been thinking about, that we've been talking about in our community. I guess the first one is, how many planets like Earth are there in our solar system and then beyond our solar system? If you watch Star Trek, it feels like every planet has life on it. But how realistic is that?
Yeah, that's such a great question, Sandy. So in terms of our own solar system, Earth is unique. There is just one Earth in our solar system. We have some planets that are similar to Earth in certain regards. If you look just outside of Earth's orbit, you see Mars. You look just inside Earth's orbit, you see Venus. And these are rocky terrestrial planets, as we call them, just like the Earth, but their histories are so different. We see basically the loss of habitability on these planets through time. So Earth has maintained its habitability, which means its suitability for life, over its 4.5 billion year history or so. Venus and Mars may have started off very Earth-like and enjoyed some measure of habitability early in their lifetimes, but Venus underwent a runaway greenhouse, which means that it got far too hot and all the water evaporated into the atmosphere and then escaped into space. Whereas on Mars, it got far too cold, and there's still a lot of water locked on that planet, but just as ice. And so we see the effects of climate change going one way or the other on these worlds, and we really gain an appreciation for how special our home planet is. Now, in terms of the rest of the universe, there could be millions, maybe even billions of Earth-like planets out there. So far, we've discovered a few dozen planets that are similar to the mass and the size and potentially the temperature of the Earth. But we don't really know that they are Earth-like in all of their details. We'll need to build a much bigger, more powerful telescope to get to know those planets a little bit better and see if they have oceans, if they have atmospheres, and if they have life.
It looks like that has sparked a question from our audience. So Moonfish, her son asked, are there any other stars similar to the sun?
That's another great question. And yes, indeed, there are many stars that are similar to the sun. Stars are mostly characterized by their mass, which is how heavy they are, how much stuff they have. And depending on that mass, they will glow at different temperatures and be different colors. And there are a lot of stars that resemble our sun, but surprisingly, perhaps to many of you, the most common type of star in our galaxy is a much smaller, much dimmer, much redder kind of star that we scientists like to call M dwarfs. We've got a whole classification of stars with different letters. They're not important, but if you ever hear a scientist talk about an M dwarf, they're really talking about the most common type of star in our galaxy. Roughly 7 out of 10 stars are these red dim M dwarfs. And these types of stars do host rocky terrestrial planets. And it's one of the biggest scientific questions to know whether or not rocky planets around M dwarfs can host life.
That's fascinating. Like, you just assume that all the stars are like our sun, but there are so many different types, and it's amazing to think about that and how that could really have implications for other sources of life. Looks like we have another great question from Joanne, whose students are studying First LEGO League Challenge and Exploration. This year's topic is submerged, and they want to know, is exploring space similar to exploring the ocean?
Oh, wow. I love this question so much. Yes, it is in the idea that when you go into space or when you go deep in the ocean, your immediate environment is not very friendly to you. Either the pressure is so low and it's vacuum, or the pressure is so high and you would get crushed, right? And so you can't really go outside of a little tin can, basically, that is protecting you from the environment. And so in outer space, that might be your space station, that may be a space shuttle. And for the ocean, for exploring especially the depths of the ocean, you need very, very hardy submersibles to be able to do that. So they are both extreme environments, extremely difficult to access, and extremely unfriendly to us because we evolved right here on the surface of our planet, blanketed by a beautiful atmosphere and not under a tremendous amount of pressure.
That makes me think, as we talk about all these wonderful planets out there in the universe, are we able to go to them? How are we going to visit other planets, or is that not something that we're able to do?
Well, there's a big difference between the planets within our solar system and the planets that orbit other stars, again, which we call exoplanets. So within our solar system, we are able to send our robotic spacecraft to go and visit these planets, to land on them, to rove upon them, to explore them for us, and then beam back data and pictures so that we can study them. We've only been able to send astronauts as far as our moon, but our robotic spacecraft are able to go to Mars and Venus and Jupiter and Saturn and even to Pluto and beyond. But when it comes to planets that orbit other stars, those planets are so far away, we have not yet been able to send anything fast enough to reach them. So we have to study those planets with our telescopes. So we let light be the messenger that tells us information about those planets. And one clever way of doing this is imagine pointing a telescope up at a star in the sky. If it has a planet orbiting it, at just the right angle, that planet will pass in front of the star once per orbit. And as the starlight streams toward us through space, some of that light will be blocked by the planet. And we're able to not only detect the planet that way, but also get to know a little bit about the planet's chemistry, because different atmospheric molecules will place different fingerprints on the light that is streaming toward us. And by looking at those fingerprints, we'll be able to know, oh, that planet's atmosphere has carbon dioxide or methane or et cetera, and begin to get to know what the air is like on that world.
That is fascinating. It's amazing how much we can learn from a shadow,
Yes.
Please make sure that you're putting your questions into the chat for Dr. Wong. We'd love to know what you're curious about. As we're kind of talking about this, we're obviously studying life on the International Space Station right now, and soon on the Gateway near the moon. How does what we're learning about astronauts living in space right now help us understand maybe how we can explore space or how we can understand other life forms from other planets? How is that useful information?
Yeah, well, the International Space Station and all astronaut missions are really tests for many important questions. One of them is whether or not we can survive in outer space, right? It's a big question because we, again, evolved here on Earth to be suited for a specific kind of environment, which space is absolutely not that environment. And so we want to know, how does the human body react when it's in weightlessness? And we also want to know how other forms of life react too, especially those that might feed us. So like, can plants grow in space? And we also are able to study how certain organisms could maybe survive journeys through outer space. So certain microorganisms can shield themselves from the dangerous radiation that is experienced in space. And by learning about how they can do that, we learn about how they might survive a transit from one planet to another. So if you imagine, for instance, some alien life emerging on Mars, and then an asteroid hits Mars and knocks a piece of Mars off, which then circles the sun for, I don't know, tens of thousands, maybe even 1,000,000 years, and then eventually crashes on Earth, could life have survived that journey? Well, that's a question that we can begin to answer by studying how life interacts with the space environment on the space station. And finally, there's a lot of Earth science that is done from the International Space Station. From that vantage point all the way up there, we're able to look down on Earth and be able to see Earth as a planet, which it absolutely is, and learn about Earth in a planetary context and understand weather cycles, climate change, and the way that we're impacting our soil and our forests and our atmosphere.
As you were talking about this, Joanne had another question from a group of students. They're working on a mission to moon challenge, and they're wondering, would you rather live on the moon or on Mars?
That's a great question. I don't know if I would necessarily want to move permanently to either one of those locations. I do really like it here on Earth, but I would love to visit Mars because it has that potential again for perhaps being very Earth-like in the past. And so it would be great to go to Mars and do a little bit of geology, take a sample or two, investigate that for signs of ancient life, fossils, for instance. Again, Mars right now is a pretty inhospitable place, but billions of years ago, there was flowing water on Mars. And the big question is, can you find in those, dried up lake beds and dried up rivers signs of long gone alien life? And that's a study that I think would be really exciting to undertake on Mars. So again, I would like to visit Mars, maybe do some science there, but I don't think I would move my entire life there. I would want to come back to Earth and share everything that I've learned here over on Mars with all of you.
That's so interesting because you mentioned that what you study can help us here on Earth in so many ways. And you mentioned climate change that happened, well, for reasons we may not fully understand on other planets. So how can astrobiology help us here on Earth to make our planet a better and healthier place to live?
Yeah, astrobiology has a lot of connections to studying life on Earth and climate. One thing to recognize is that we use very similar climate modeling tools to understand exoplanet habitability and the habitability of ancient Mars and ancient Venus as the tools that we use to predict climate change here on Earth. It's basically simulating the atmosphere and the changes to the atmosphere and the changes to the temperature that are induced by those atmospheric changes. And so when we ask the question, is an exoplanet habitable for life? It's a very similar kind of calculation to knowing how the habitability of our very own planet will change given a certain amount of CO2 emissions over time. Another big thing that astrobiologists are super interested in is extremophiles, which are organisms that love living in extreme environments and figuring out who can live in those harsh environments and how they are adapted to those environments. And that's important for astrobiology because what may seem extreme for us as human beings may actually be the norm on a different planet, on a very dry world like Mars, or an icy world like Jupiter's moon Europa, or an acidic planet like Venus. That may be the norm. And so understanding how life is adapted to those types of environments can help us anticipate what kind of life to look for. And then there's this whole concept of habitability, right? So when we talk about habitability, it's a word that we talk about a lot in astrobiology. In environmental science and climate science, we often talk about this word sustainability. But I think one thing that maybe we can learn from astrobiology is switching the word sustainability for habitability. The reason is subtle, and it's because the word sustainability, it's something, it connotes this idea that the environment is something separate from us, that we can sort of like impact, but we're not a part of. It's the environment is this thing that we want to sustain only. But habitability, this term from astrobiology, really acknowledges the fact that the environment is our home, that we play a part in it, that we're a part of the home, and that we are a part of the home for other organisms too, and that everything is linked together. It's not separate. And when our environment suffers, our home suffers as well.
That is such a great point. And as we're already kind of running out of time, I am going to encourage everyone that if you didn't get to ask a question today, make sure you post it in our community. Our community lab for Down to Earth is a safe environment for kids and adults to share their ideas and to ask questions. And I promise I will email Dr. Wong with any questions that you share there. Before we kind of wrap up today, is there anything else that you want to share with our young learners to hopefully inspire them to follow in your footsteps?
Sure, yeah. So I have one last slide that I'd like to share with everybody. So I want to end with this thought that we are life in space. A lot of people ask me as an astrobiologist, how can you study astrobiology, Mike, when we haven't yet discovered life out there? And I like to remind everybody who asks me that question that we have actually found life in space. We've discovered that we are life in space. We are travelers on this planet-sized spaceship that we call Earth. And when we are looking out there for life beyond Earth, we're basically looking for other Earth-sized spaceships with their own travelers on them. And so astrobiology and earth scientists use very similar tools to understand in astrobiology what we call planetary habitability, the potential for life elsewhere, and also climate change, how life will be impacted in certain possible Earth futures, depending on what we choose to do in the present moment. And also, astrobiology is really instrumental in trying to advance this idea of Earth as a living planet, that we need to think about life at the planetary scale, and that we are not separate from the natural environment and separate from our planet, but that we are part of it, that we are children of Earth, that we are Earth stuff, and that we are the latest chapter in a long story of co-evolution between life and our planet. You can't separate our story from the story of our Earth. And so there are many, many, many climate connections to the cosmic conundrum of, is there life elsewhere? And as we think about trying to look for other habitable worlds, we are forced to reflect upon how we are influencing the future habitability of our own.
That is so amazing. And it really puts things into perspective. I forget sometimes that we're on a giant rocky spaceship. And, so that is such a great reminder. Thank you so much for being here, Dr. Wong. I really appreciate your insights. I really appreciate your knowledge and for the fact that you took the time today to share with us. Remember, folks, if you didn't get to ask a question today, you can certainly post it in our community lab. I do want to do a quick introduction of our design challenge for the week, because this is a really fun way for everybody to get involved. So I'm going to go ahead and share my screen. Here we go. All right, so this week, our design challenge is stellar health, how to train like an astronaut. So first, you're going to learn all about how they exercise on the International Space Station, because as you may see, our astronaut here is wearing a harness. And the first question we have for you is, why do you think she needs one? So please go and check that out. You can find that on our website at sciencefriday.com/down-to-earth. And just read through all about what it takes to exercise like an astronaut. You're going to get to try out some fun exercises yourself. And then our design challenge is to take everything you learned today from Dr. Mike, Dr. Wong, and from our resource, and you are going to have to develop an exercise routine that people could use inside if they're dealing with something like a heat wave due to climate change or air pollution due to environmental concerns. So you can design a piece of equipment that will help people exercise indoors, or come up with your own exercise routine for your friends and family. And when you do that, we would love to see what you make on our community lab. So it uses very simple materials. Anyone can try it out. And I really hope that you will head on over to sciencefriday.com/down-to-earth and give our design challenge a try. So last thoughts, anyone want to share any last questions or thank yous for Dr. Wong? I see that Jess thinks that astrobiology is the coolest science, hands down. I think that's very, very true. Again, thank you so much for being here, everyone. Please do go and sign up so you get regular reminders about what's going on. We also have a feedback survey that we would ask you to fill out for this event so that we can continually improve and get better at what we do. And I see Moonfish is saying, thank you, Dr. Wong and Sandy. This was great. I think it was great too. And I learned so much from you today, Dr. Wong. Thank you. All right, everyone. Unless there are any other questions, I think we're going to sign off for the day. And we will see you again next week at the same time, 1:45 p.m. Eastern, 10:45 a.m. Pacific time. Please make sure that you come on back and join us. All right. I think we're all good for the day. Thank you so much, everybody.